In this lesson, we will look at the particle on a sphere. In a previous lesson, we examined the quantum mechanical description of a simple system known as the particle on a ring, where the particle is confined to move on a circle on the xy plane. Let's first review what we learned from that lesson. We learned that using polar coordinates was convenient for solving the Schrödinger equation, h hat psi equals E times psi. As shown in this diagram, the Cartesian coordinate x is equal to r, the radius of the circle, times the cosine of phi, the angle between the radius vector and the positive x-axis. And the Cartesian coordinate y is equal to r times the sine of phi. The Hamiltonian operator then simplifies to negative h bar squared over 2I times the second derivative with respect to phi, where uppercase I is the moment of inertia, which is equal to the mass times the square of the radius. We learned that Lz hat, the quantum mechanical operator for the z component of the angular momentum, is h bar over the imaginary number I times the derivative with respect to phi. We also learned that the angular momentum is directed in either the positive z direction or the negative z direction. The angular momentum vector has 0 components along the x and y axes. It should be easy to see that the Hamiltonian operator is just equal to the square of the Lz operator over 2I. And that the h hat and Lz hat operators commute. Because h hat and Lz hat are Hermitian operators and they commute, they must have in common a complete set of eigenfunctions. The eigenfunctions in the common complete set are of the form 1 over the square root of 2 pi times e to I times m sub l times phi, where the quantum number m sub l is restricted to integer values. The eigenvalues of the Hamiltonian operator, the allowed energies, are m sub l squared times h bar squared over 2I. And the eigenvalues of the Lz operator, the allowed values of the z component of the angular momentum, are m sub l times h bar. In this lesson, we will examine the particle on a sphere, which is just the three-dimensional version of the particle on a ring. Just like for the particle on a ring, it is convenient to do a transformation of coordinates to describe the particle on a sphere. Since we're dealing with 3 dimensions, we need one more coordinate. We replace the Cartesian coordinates x, y, z by spherical polar coordinates r, theta, and phi. Let's examine the diagram shown here to see how Cartesian coordinates x, y, z are related to spherical polar coordinates r, theta, and phi. Consider this location. The coordinate r is defined as the distance of this location from the origin. The value of r goes from 0 at the origin to infinity when it's very, very, very far away. So, r is a non-negative number. It should be easy to show, using the Pythagorean theorem, that r is equal to the square root of the sum of x squared, y squared, and z squared. What is the value of r for any point on the sphere shown here? Let's examine the figure. We can see that the 2 labeled points are 6 units away from the origin. All points on a sphere are equidistant from the center. So, r is equal to 6. An equation that says that r is equal to a constant describes a spherical surface. Now, let's talk about the theta coordinate. The coordinate theta is the angle between the positive z-axis and the line joining the location to the origin. Here's the z-axis. For this location, here's the line from the origin. The angle between the 2 lines is theta. It should be easy to see that cosine of theta is equal to z over r, which means that z is equal to r times cosine theta. For any location, the value of theta can be anywhere from 0 to pi. If a point is on the positive z-axis, theta is equal to 0. If a point is on the negative z-axis, theta is 180 degrees or pi radians. We need to sweep an angle of 180 degrees from the positive z-axis to locate a point on the negative z-axis. To locate a point on the xy plane, we need to sweep an angle of 90 degrees, or pi over 2 radians, from the positive z-axis. What do you think are the values of theta for locations above the xy plane? Like the point shown here, we would need to sweep an angle that is less than 90 degrees.
How about locations below the xy plane?
At these locations, theta would be between 90 and 180 degrees, or between pi over 2 and pi radians. All points with the same theta lie on the surface of a vertical cone, except if theta is 0, pi over 2, or pi.
The tip of the cone is at the origin.
Any line, from the origin to any of the points on the conical surface, will be at the same angle with respect to the positive z-axis.
In the example here, if the angle between this line and the positive z-axis is 45 degrees, or pi over 4, then we can represent the cone by the equation theta equals pi over 4.
Any point on this conical surface has a theta equal to pi over 4. What do you think is the equation that describes this cone, which opens downward if a line, from the origin to any of the points on the surface, forms a 30-degree angle from the negative z-axis?
We just need to determine the angle from the positive z-axis.
30 degrees is pi over 6. So, the angle from the positive z-axis is 5 pi over 6.
This cone is described by the equation theta equals 5 pi over 6.
Any point on this conical surface has a theta equal to 5 pi over 6.
Now let's take a look at coordinate phi. For a point at this location, the perpendicular projection on the xy plane, shown here as P,
can be easily shown to be at a distance equal to r times sine of theta
from the origin.
Phi is the angle between the positive x-axis and the line from the origin to point P. The angle phi can be anywhere from 0 to 2 pi. And it can be shown that x is equal to r times sine theta times cosine phi. And that y is equal to r times sine theta times sine phi. All points on a planar surface which has the z-axis on one edge have the same phi coordinate.
What do you think are the values of phi for the planar surfaces shown here?
If the perpendicular projection of a point on the xy plane lands on the positive x-axis, then phi is 0.
Therefore, for points on the xz plane, when x is positive, phi is 0. Imagine this surface as a door hinged to the z-axis.
Now, imagine swinging the door counterclockwise by 60 degrees. Then, all points on the door will now have a phi coordinate equal to pi over 3 radians. 60 degrees is pi over 3 radians.
All locations on a spherical surface are equidistant from the center of the sphere.
So if we set the origin at the center of the sphere, then r is the same for any point on the sphere. Imagine the Earth as a perfect sphere. Of course, it's not, but assume that it is.
What would all locations at the same latitude have in common? The latitude at a given location is the angle between
the line from the center to that location, and
the line from the center to any location on the equator.
Therefore, all locations with the same latitude will have the same theta. The only difference between latitude and theta is that latitude is the angle relative to the equator, while theta is the angle relative to the North Pole. Note that all locations at a given latitude constitute a circle.
Think of this circle as the intersection of a conical surface with the sphere.
Remember that all points on a conical surface have the same theta. Points on the cone that are equidistant from the tip of the cone form a circle.
How about all locations at the same longitude? What do they have in common? They will all have the same phi.
If we define phi as 0 at the prime meridian, then
at the international dateline,
phi will be 180 degrees, or pi radians. It can be shown that there are solutions to the Schrödinger equation that can be written as a product of
a function of theta and a function of phi.
These solutions are known as the spherical harmonics. The spherical harmonics form a complete set of eigenfunctions, not just for the Hamiltonian operator, but also for the L-squared and Lz operators. The L-squared operator is the quantum mechanical operator for the square of the magnitude of the angular momentum.
And the Lz operator is the quantum mechanical operator for the z component of the angular momentum. Two quantum numbers, L and m sub L, are associated with each spherical harmonic function.
The restrictions on the quantum numbers are as follows. The quantum number L, known as the orbital quantum number, is restricted to non-negative integers. For a given L, the quantum number m sub L is restricted to integer values from negative L to positive L. We will encounter spherical harmonics again when dealing with the hydrogen atom later in the course, and we will learn that the m sub L quantum number gives us information about the magnetic properties of atoms. It is for this reason that the m sub L quantum number is also known as the magnetic quantum number. The factor that depends only on phi turns out to be the same as the wave functions for the particle on a ring confined to the x-y plane. If you recall, each of these wave functions is associated with an m sub L quantum number. The factor that depends only on theta is defined by quantum number L and the absolute value of m sub L. The spherical harmonics are typically represented by uppercase Y, with the quantum numbers indicated as subscripts. Given the preceding information, is this statement true or false? For a particle on a sphere, it is possible to precisely determine the energy, the magnitude of the angular momentum, and the z component of the angular momentum at the same time. The answer is true. When operators have a common complete set of eigenfunctions, then they commute with each other. Therefore, we can say that the commutator of h and L squared is 0. The commutator of h and Lz is 0. And the commutator of L squared and Lz is 0. The complete set of eigenfunctions they have in common are the spherical harmonics. When operators for a dynamical property commute, it is possible to precisely measure the corresponding eigenvalues at the same time. Recall that the eigenvalue for the Hamiltonian operator is the energy. The eigenvalue for the L squared operator is the square of the magnitude of the angular momentum. And the eigenvalue for the Lz operator is the z component of the angular momentum. Note that if you can precisely determine the square of the magnitude of the angular momentum, it also means that you can precisely determine the magnitude itself, since it's just the square root of the square. The allowed energies for a particle on a sphere can be shown to depend on quantum number L. The allowed energies are equal to L times L plus 1 times B. As with the particle on a ring, B is the rotational constant, which is equal to h bar squared over 2I. Where I is the moment of inertia, which is equal to mass times the square of the radius of the sphere. So what would be the energy for the third excited state? Well, the lowest allowed value for L is 0. So, the lowest allowed energy, the energy for the ground state is 0 times 0 plus 1 times B, or 0. We get the first excited energy level when L is equal to 1. 1 times 1 plus 1 times B is 2B. It should be easy to show that the second excited energy level is 6B. And the third excited energy level is 12B. What do you think happens to the gap between allowed energy levels as L increases? It should be easy to show that E for level L plus 1 minus E for level L is equal to 2 times B times L plus 1. In other words, the gap between adjacent energy increases at higher energies. What is the degeneracy of the first excited energy level? The formula for allowed energies is L times L plus 1 times the rotational constant B. And the first excited energy level, with quantum number L equal to 1, is 2B. Recall that for a particle on a sphere, a state is defined by two quantum numbers, L and m sub L. And that for a given L, the allowed values of m sub L are integers from negative L to positive L. So, for L equals 1, there are three possible quantum states. L equals 1 with m sub L equals negative 1. L equals 1 with m sub L equals 0. And L equals 1 with m sub L equals positive 1. In other words, there are three ways that the particle on a sphere can have an energy equal to 2B. There are three quantum states with energy equal to 2B. We say that the degeneracy of the energy level associated with L equals 1 is 3. Lowercase g is typically used as the symbol for degeneracy. We specify the quantum number that determines the energy as a subscript. When we say that g sub 1 is equal to 3, we mean that the degeneracy of the energy level associated with the quantum number L equals 1 is 3. In general, for a particle on a sphere, the degeneracy of the energy level associated with quantum number L is 2L plus 1. It's just the number of possible m sub L values for a given L value. Earlier, we saw that the L squared and LZ operators commute and have a common complete set of eigenfunctions, which happens to be the spherical harmonics. The eigenvalues can be shown to be L squared times L squared plus 1 times h bar squared, and m sub L times h bar for the L squared and LZ operators, respectively. For example, what are the magnitude and z components of a particle in quantum state L equals 3 and m sub L equals -2? The square of the magnitude of vector L is given by the eigenvalue of the L squared operator. It's L times L plus 1 times h bar squared. In this case, L equals 3. So the square of the magnitude of vector L is 12h bar squared. Taking the square root, we find the magnitude of vector L to be square root of 12 times h bar. The z component is the eigenvalue of the LZ operator. It's m sub L times h bar. In this case, m sub L is -2. Therefore, the z component is -2 times h bar. Let's draw an arrow to represent this angular momentum vector. Here's the z-axis. Here's the x-y plane. And here's an arrow with a length equal to square root of 12h bar. And z component of -2h bar. It can be shown that the L squared operator also commutes with the Lx and Ly operators. Lx and Ly are the x and y components of the angular momentum. Does this mean that the L squared and Lx operators also have a common complete set of eigenfunctions? How about the L squared and Ly operators? The answer to both questions is yes. When two operators commute, they have a common complete set of eigenfunctions. However, it's a different set for L squared and Lx. Not the spherical harmonics. It's also a different set for L squared and Ly. Again, not the spherical harmonics. It turns out that the Lx, Ly, and Lz operators do not commute. The commutator of Lx and Ly is not 0. It is equal to the imaginary number I times h bar times the Lz operator. Similarly, the commutator of Ly and Lz is not 0. It is equal to I h bar times Lx. And the commutator of Lz and Lx is equal to I h bar times Ly. This means that it is not possible to find a common complete set of eigenfunctions for any two components. It also means that if we try to measure angular momentum, we can precisely determine the magnitude. And only one of the components at the same time. If the quantum state is described by a spherical harmonic, that would be the z component. A spherical harmonic describes a particle with an angular momentum that has a well-defined magnitude and a well-defined z component. But we have absolutely no idea what the x and y components are. Consider the diagram shown here. Imagine this is a circle on the xy plane. If m sub L is 0, then the z component is 0. If we represent the angular momentum vector by an arrow with its tail at the origin, then the tip of the arrow can be anywhere on this circle on the xy plane. It could be here, or here, or here. We don't know the x and y components of the vector. If quantum number L is 1, then the length of the arrow is square root of 2 times h bar. It's the same regardless of where it's pointing, since the magnitude of the vector is well defined. If m sub L is non-zero, then the angular momentum vector can be described as precessing in a cone of uncertainty around the z-axis. Imagine this circle as above the xy plane and parallel to the xy plane. If L equals 1, then the length of any vector, with tail at the origin and tip at the circle, like this one, is square root of 2 times h bar. Because we don't know the x and y components, the tip of the arrow could be anywhere on this circle. It could be here, or here, or here. The spherical harmonics are typically plotted as three-dimensional surfaces to make them easier to visualize.
How do we interpret the plots?
The distance of the point on the surface from the origin is the absolute value of the spherical harmonic for the theta and phi associated with that point.
If the plot is color-coded, different colors represent different algebraic signs.
The color coding allows us to easily identify nodes. The locations where the function changes algebraic signs if the values are real numbers.
Note, however, that values of spherical harmonics are complex numbers in general.
The values are real only if quantum number m sub L is 0.
Let's look at the examples here.
For these examples, m sub L is 0. And the quantum number L, from top to bottom, is 0, 1, 2, and 3. For L equal to 0, the plot looks like a sphere. This means that the absolute value of the spherical harmonic is constant, since the points on a spherical surface are equidistant from the origin. For L equal to 1, the plot shows two lobes, colored differently. This suggests that the function has one node between the two lobes. In fact, this node is the xy plane, which corresponds to all locations with theta equals 90 degrees. For L equal to 2, the plot shows two lobes and something that looks like a donut between the two lobes. The color coding suggests that there are two nodes. In fact, those nodes are conical surfaces. The node between the top lobe and the donut is a conical surface for which theta is 54.7 degrees. And the node between the donut and the bottom lobe is a conical surface for which theta is 54.7 degrees from the negative z-axis, or 125.3 degrees from the positive z-axis. For L equal to 3, the plot shows two lobes and two donuts. The color coding suggests that there are three nodes. Two of the nodes are conical surfaces between each lobe and the neighboring donut. And the third node is the xy plane between the donuts. In general, if m sub L equals 0, we find that there are L conical nodes if quantum number L is even. If quantum number L is odd, then the xy plane is a node, and there are L-1 conical nodes. In either case, the total number of nodes is L. Here are some more examples. The image here is from Eric Weisstein's document posted on Wolfram.com. These images were generated setting the distance from the origin equal to the square of the absolute value of the spherical harmonic. There is no color coding for algebraic sign since the square of the absolute value is always positive. These are the plots for m sub L equals 0, for L equals 0, 1, 2, and 3. Notice that these are very similar to the plots we saw earlier. It's easy to see that the number of nodes is equal to L. Here are the plots for m sub L equals +1, for L equals 1, 2, and 3. The plots for m sub L equals -1 are the same. Here are the plots for m sub L equals +2, for L equals 2 and 3. The plots for m sub L equals -2 are the same. Note that when m sub L is not equal to 0, the z-axis is a node. For example, when L equals 1 and m sub L equals +1 or -1. This dimple is due to the node at the z-axis. In addition to the z-axis, we can also see additional nodes. The number of additional nodes is L minus the absolute value of m sub L. For L equals 1 and m sub L equals +1 or -1. L minus the absolute value of m sub L is 0, and we don't see an additional node. However, for L equals 2 and m sub L equals +1 or -1. L minus the absolute value of m sub L is 1, and we see one additional node, the xy plane. And, for L equals 3 and m sub L equals +1 or -1. L minus the absolute value of m sub L is 2, and we see two additional nodes. One conical surface that opens upward, and another conical surface that opens downward. Let's see what the expressions for the spherical harmonics tell us about the probability density for a particle on a sphere. Let's first look at cases where m sub L is equal to 0. If L is 0, then the spherical harmonic is equal to a constant, 1 over square root of 4 pi. Since the function does not depend on theta or phi, neither does the square of the absolute value of the function. We can say that there is a uniform probability everywhere on the sphere. We can also see that, obviously, the function has no node. If L is 1, then the spherical harmonic is square root of 3 over 4 pi times cosine of theta. We can see that the spherical harmonic is 0 when cosine theta is 0. This occurs where theta is 90 degrees or pi over 2, which corresponds to the xy plane. The intersection of the xy plane and a sphere is the sphere's equator. In this quantum state, defined by L equals 1 and m sub L equals 0, there is zero probability of finding the particle at the equator. The equator is a node. The maximum value of the probability density function occurs at the north and south poles, where theta is 0 and pi. And cosine theta is +1 and -1. So, for this quantum state, the most probable location for the particle on a sphere is at the poles. The probability diminishes as you approach the equator. If L equals 2, then the spherical harmonic is square root of 5 over 16 pi times 3 cosine squared theta minus 1. We get a node when 3 cosine squared theta minus 1 is equal to 0. This means we get a node when cosine theta is equal to 1 over square root of 3, or -1 over square root of 3. The inverse cosines of these two numbers give us the angle theta for the two conical nodes we saw earlier. For a particle on a sphere, at latitudes 54.7 degrees from either North Pole or South Pole, the probability of finding the particle is 0. The nodes are circles, or the cones intersect with the sphere. One node is above the equator and the other is below the equator. If we examine this function, we will find that the maximum probability density occurs at the poles, decreases as you approach the nodal latitudes where it becomes 0, increases again as you approach the equator, then decreases again as you move away from the equator toward the other nodal latitude. Let's look at two more examples. For L equals 1 and m sub L equals +1, the spherical harmonic is given by this expression. For L equals 1 and m sub L equals -1, here's the expression for the spherical harmonic. Notice that these two expressions are complex, due to m sub L being non-zero. Remember that phi-dependent factor is e to the I times m sub L times phi. If we take the square of the absolute value of either of these functions, we get the same expression. The probability density function is the square of square root of 3 over 8 pi times sine theta. The same can be said for any pair of spherical harmonics that have the same L and absolute value of m sub L. Now, let's examine this function. We can see that the probability density is 0 where theta is 0 and where theta is pi. Because at these angles, sine of theta is 0. This locations correspond to the positive z and negative z axis. In other words, in these quantum states, the probability of finding the particle on a sphere at the North Pole is 0. The probability is also 0 at the South Pole. Where is the most likely location of the particle? That would be when sine theta is 1. Sine theta is 1 when theta is pi over 2, which is the xy plane. For a particle on a sphere, the intersection of the xy plane and the sphere is the equator. Recall the three-dimensional surface plot for the probability density that we saw earlier. Now, we can understand the dimple at the positive z-axis direction and the bulge around the equator. If we could manipulate the view, we should also see a dimple in the negative z direction. In the lesson on the particle on a ring, we saw that we could replace pairs of complex wave functions associated with non-zero m sub L by equivalent pairs of real wave functions by taking appropriate linear combinations. We can do the same for spherical harmonics. The real pairs are, in fact, preferred by chemists as they allow us to more easily visualize bonding in molecules in terms of atomic orbitals. Consider the wave functions for L equals 1, with m sub L of +1 and -1. These wave functions are complex because of the phi-dependent factor.
Since these two wave functions are degenerate eigenfunctions of the Hamiltonian operator, any linear combination would also be an eigenfunction of the Hamiltonian operator.
These two linear combinations, shown here as py and px, can be shown to be real. Multiplying the sum of y1 plus 1 and y1 minus 1 by I over square root of 2 gives us square root of 3 over 4 pi times sine theta times sine phi. Multiplying the difference of y1 plus 1 and y1 minus 1 by negative 1 over square root of 2 gives us square root of 3 over 4 pi times sine theta times cosine phi. We will see these functions again when we talk about atomic orbitals. Note that sine theta times sine phi is equal to y over r. Hence, the name py. Similarly, the name px is based on the fact that sine theta times cosine phi is x over r. Incidentally, the spherical harmonic y10, which is real, is equal to a constant times cosine theta. Cosine theta is equal to z over r. So here, we can see similarities in the expressions for py, px, and y10. In fact, y10 is also referred to as pz. This is why the 3D surface plots for these orbitals look very similar. They only differ in the orientation of the lobes. Note that, as in the particle on a ring, the z component of the angular momentum is no longer well defined for quantum states defined by the px and py functions. Here's a comparison of the three-dimensional surface plots of probability density for wave functions with L equals 1. These are probability density functions for y10, y1 plus 1 and y1 minus 1. The probability density function is the same for m sub L plus 1 and minus 1. And here are the probability density functions for the real spherical harmonics with L equals 1. The pair px and py is obtained by taking appropriate linear combinations of the y1 plus 1 and y1 minus 1. Let's examine the plot for px. Here's the z-axis. Here's the y-axis. And here's the x-axis. The two lobes are centered on the x-axis. And the y-z plane is a nodal plane. For the y-z plane, the phi coordinate is either 90 degrees or 270 degrees. The lobes for the py are centered on the y-axis. The xz plane is a nodal plane. For the xz plane, the phi coordinate is either 0 or 180 degrees. y10 and pz are the same function. The plot has two lobes centered on the z-axis. The xy plane is a nodal plane. For the xy plane, the theta coordinate is 90 degrees. Here's how real spherical harmonics are obtained for L equals 2. Linear combinations of spherical harmonics with m sub L equals plus 1 and minus 1 yield a pair of spherical harmonics known as dyz and dxz. Linear combinations of spherical harmonics with m sub L equals plus 2 and minus 2 yield a pair of spherical harmonics known as dxy and dx squared minus y squared. The spherical harmonic with L equals 2 and m sub L equals 0 is real and is also known as dz squared. Here are the three-dimensional surface plots for the probability density functions for L equals 2. These are the ones with well-defined m sub L. Because the functions are complex for non-zero m sub L, the probability density function is the same for m sub L plus 1 and minus 1. And it's the same for m sub L plus 2 and minus 2. These are the surface plots for the probability density functions for the real spherical harmonics. The dz squared is identical to y20. It has two lobes separated by a donut. There are two conical nodes, one separating the top lobe from the donut and the other separating the bottom lobe from the donut. The dyz has four lobes, with each lobe wedged between the y and z axes. Here's the positive z-axis. Here's the positive y-axis. And here's the positive x-axis. We can see that the xy and xz planes are nodal planes. The dxz has four lobes, with each lobe wedged between the x and z axes. The xy and yz planes are nodal planes.
If you imagine rotating the surface plot for dxz by 90 degrees about the z-axis, you'll get the surface plot for the dyz. The dxy has 4 lobes, with each lobe wedged between the x and y axes. The xz and yz planes are nodal planes. And lastly, the dx squared minus y squared has 4 lobes, with each lobe centered on either the x or y axis. If you imagine rotating the surface plot for dxy by 45 degrees about the z-axis, you'll get the surface plot for dx squared minus y squared. There are 2 nodal planes intersecting at the z-axis. Points on one of these 2 planes will have a phi coordinate equal to either 45 degrees or 45 plus 180 degrees. Points on the other plane will have a phi coordinate of either 135 degrees or 135 plus 180 degrees.